Good morning, ladies and gentlemen. My name is Karen Lombard, and I'm a physical sciences teacher at Unisi High School. Today, we'll be looking at one of the topics in chemistry that might not be considered a difficult topic. And I know that I'm now speaking to young ladies and gentlemen who want to excel in this subject. And usually, we would focus on the more difficult topics for you. The reason that we have chosen reaction rate is because it's a section of work where you can very easily accumulate a large number of marks. So we tend to sometimes forget about the simpler sections of work in our enthusiasm to master the more difficult sections. So I'm not saying that this is an easy section of work, but it might be easier compared to some of the other sections that we have looked at. But it is definitely a section where you can accumulate marks and push your symbol up from one symbol to the next. And to achieve that goal that you have set for yourselves at the beginning of the year. So reaction rate. Let's just get clear in our minds first before we start here what we're actually dealing with. Please remember that anything where the word rate appears has got to do with divided by time or per unit time. So we're looking not at how much of a substance is formed during a chemical reaction, but rather how quickly that substance is going to be formed. We are also going to be looking at what factors influence the rate of a chemical reaction. And then we'll be using what is called the collision theory to then help us to substantiate or back up our discussions on those different factors. All right, so what macroscopic properties are going to influence the rate of a chemical reaction? The first one is temperature, followed by the concentration of the reactants, then the nature of the reactants, which we're not going to deal with particularly much. I will discuss what it is, and then we're pretty much not going to look at it in too much detail. We are going to look at the influence of a catalyst on a chemical reaction, and then finally, the surface area of the reactants in a chemical reaction. So those are the 5 macroscopic factors that can influence the rate of a chemical reaction. Then the collision theory looks in detail at how each of those factors influences the rate of a chemical reaction. So for each of those 5 factors, we will then take the collision theory and apply the collision theory to each of the factors and their effect on the rate of a chemical reaction. Very importantly, please do not confuse the collision theory with the kinetic theory. Now, the kinetic theory was done in grade 10, and we also touched on it in grade 11 with the gas laws, and even this year when we did the physical properties of organic substances. But the kinetic theory is not the same as the collision theory, so please just do not get the two of them mixed up in your minds. All right, let's just look at the kinetic theory quickly. The kinetic theory speaks about the fact that all matter is made up of particles, and that these particles are in constant motion, and that results in pressure, volume, etc., and the kinetic energy of particles. The particles collide with one another and with the sides of the container. Now, if we think back to grade 11, it is these collisions of particles with the side of the container that cause pressure in a gas. So gas particles are constantly in motion, and as they move, they are colliding with the sides of the container. And each of those collisions then results in pressure. All right, so that is what gives gases pressure. And finally, the particles exert forces on each other. We spoke about intermolecular forces in detail in grade 11, and then again in organic chemistry in grade 12. But more importantly for this section of work is the collision theory. Right. Now, to start off with, the collision theory looks into microscopic properties that determine whether, as well as how fast, a reaction will take place. Now, when you're in the lower grades, when you were doing natural sciences in grades 7, 8, 9, your teacher may have done a number of chemical reactions with you. And we always kind of just assumed that if you put 2 chemicals together in the test tube, a reaction will occur. But we didn't realize that so many factors have to be considered before a chemical reaction will actually take place. And the collision theory explains to us why sometimes a chemical reaction does take place and at other times no reaction occurs at all. Now, one of the most important terms that you're going to look at in the collision theory is effective collisions. Now, collisions can occur, right? But whether they are effective or not will determine whether a chemical reaction occurs. So whenever two particles of reactants collide with each other, doesn't mean that it will result in a chemical reaction. The collision between those two particles has to be effective. Now, what does it mean for a collision to be effective? Two things. First of all, the particles have to collide with sufficient kinetic energy. Now, remember that kinetic energy is the movement energy, and if we go back to grade 10, we learned that temperature is a measurement of the average kinetic energy of the particles of a substance. So please keep that in mind as we discuss that. So when two particles collide, they have to collide with sufficient kinetic energy. Secondly, the molecules have to collide with the correct orientation. Now, orientation is simply a fancy word for positioning. So when those two particles collide, they have to collide positioned correctly relative to each other. And that will then give us correct orientation. So let us look at those two factors now in a little bit more detail. The reacting particles must have sufficient kinetic energy. But now the question is, what is sufficient? What is enough? What makes the collision have sufficient kinetic energy? Now, to understand that, we need to go back to grade 11. And this section of work is mentioned in your exam guidelines, and it does have grade 11 written next to it. Last year, we looked at the energy involved in chemical reactions. And we said during a chemical reaction, existing bonds first need to be broken. Right. If you are dating someone and you see someone that you kind of like, you cannot start dating the new person until you've broken the bonds with the previous person. It's just not right. Now, in chemistry, the same thing happens. If I have two molecules that want to react with each other, the existing bonds in those molecules first have to be broken before new bonds can be formed. And to break those existing bonds takes energy, right? It takes energy to break those existing bonds. And that energy is called activation energy. And we did that term last year in grade 11. So activation energy is the minimum energy required to get a chemical reaction going. In other words, the minimum energy required to break existing bonds that may exist. So let's go back to that term that we've been talking about. What is sufficient kinetic energy? Sufficient kinetic energy means that the particles need to have energy that is either equal to or greater than the activation energy for that specific reaction. If their kinetic energy is less than activation energy, the two particles will collide and simply bounce off of each other and no reaction will occur. If, however, the kinetic energy of that collision is greater than activation energy, then there's a possibility that a chemical reaction will occur. Right, I'm not going to read through all of this. It is a summary, and I will show you where I got that summary from at a later stage. All right, in order to react, colliding particles must have a total kinetic energy equal to or greater than the activation energy for the reaction. And that's the most important thing you need to remember. What is sufficient kinetic energy? Energy that is equal to or greater than the activation energy for that reaction. All right, this slideshow that I'm now going to show you comes from the Free State Department of Education, so I'm just acknowledging that I am using their work. And it gives you a beautiful summary together with pictures of what happens during an effective collision, what happens when a chemical reaction does occur. This is just to give you an idea of where we're going. What are we aiming for during this section of work? And this will come from your exam guidelines. You must be able to define reaction rates. As always, your definitions are important. State the factors that influence the rate of a chemical reaction. Be able to describe the collision theory. State conditions needed for an effective collision to take place. We've just mentioned that. Sufficient kinetic energy and correct orientation. Use the collision theory to explain how the 4 macroscopic factors that we discuss here are going to influence the rate of a chemical reaction. So use your exam guidelines to be sure that you know how to use the collision theory to discuss each of these macroscopic factors that we will be looking at. What is the rate of the reaction? We've already discussed that. It's not about how much of a product is formed, but how quickly that product is formed. This just gives you an idea of different reaction rates. If I look at rocks outside, those rocks have changed shape over the years. Their chemical composition has changed because of weathering. But it's a chemical reaction that has taken decades or even centuries to occur. So in other words, this would be a chemical reaction that has a very, very low rate of reaction, a very low reaction rate. Rusting. If you leave a bicycle outside for too long, eventually the metal is going to rust. But again, it is a slow chemical reaction, low reaction rate. Cooking, slightly quicker. And then explosions. An explosion is a chemical reaction that takes place in milliseconds, in fractions of a second. So in other words, the rate of an explosion, the rate of that chemical reaction would be incredibly high, very fast chemical reaction. Right, the macroscopic factors that we're going to look at, just to recap, the nature of the reactants, the concentration of reactants, temperature, surface area, and the presence of a catalyst during the chemical reaction. Right. This question comes out of the Macmillan textbook, and I just want you to focus on one of the questions quickly, just at question 1. It says, in the following chemical reaction, state 4 ways in which the rate of the reaction can be increased. Now, we've just named 5 macroscopic factors. Let's look at them again. Nature, concentration, temperature, surface area, and catalyst. Now, which 4 of these is going to be able to increase the rate of that first reaction? Now, to be able to answer the question, you need to be able to understand what each of these macroscopic factors is. First of all, the nature of the reactants. Now, ladies and gentlemen, the nature of the reactants refers mainly to the type of molecules that you are dealing with as reactants. So, for example, water is a fairly simple molecule. There are only the bonds between the oxygen and the hydrogen atoms that need to be broken before a new chemical reaction can occur. If, however, you have got an organic molecule that consists of numerous bonds, some of which are double bonds, some of which are triple bonds, it is a much more complex molecule, which means that it is not going to react as easily because there are more bonds that need to be broken. So nature of reactant refers to the type of reactant that you are dealing with. And we are very seldom going to look at the nature of the reactant because it's not something that we can manipulate during a chemical reaction. So we are going to focus on concentration, in other words, the number of moles per volume. Grade 11 revision. Grade 11 comes back to haunt you a lot in grade 12. Concentration is equal to the number of moles in a specific volume. So the more moles of a substance, and remember a mole is simply an amount of substance. So the more particles of the substance that you have in a certain volume, the higher your concentration will be, which results in a higher reaction rate. Increase of temperature, increase of surface area, and the presence of a catalyst. So which 4 are going to influence the following reaction? Zinc reacts with hydrochloric acid to give zinc chloride and hydrogen. First of all, I can increase the temperature of my hydrochloric acid. That would increase the rate of this chemical reaction. So the first one would be temperature. Secondly, I could increase the concentration of my aqueous hydrochloric acid solution. So I could increase concentration, more particles available to take part in the reaction. Thirdly, I could take that zinc, which is probably in chunks of zinc, fairly big pieces, and I could grind it into a powder. So in other words, I influence surface area. And finally, I could add a catalyst to the reaction, which would increase the rate of that chemical reaction. Now, how do I know if I've increased the rate of a chemical reaction? I need to know how to calculate the rate of a chemical reaction. There's a number of ways of doing it. The easiest method, reaction rate, is change in concentration of reactants over time. So how quickly is my reactant being used up? That would give me a reaction rate. Or I can calculate the change in concentration of product over a period of time. In other words, how quickly is my concentration of product increasing during the chemical reaction? We can also use the volume of gases to determine a reaction rate, but I'll show you an example of that in a while. All right, now let's use the collision theory to explain how each of those macroscopic factors influences the rate of a chemical reaction. Remember, what are the two factors in the collision theory? First of all, the reacting particles have to have sufficient kinetic energy, enough kinetic energy, and secondly, they have to have the correct orientation. Now, this is a graph that should look familiar to you from last year. Right, this is a potential energy graph for a chemical reaction. Now, my question for you is, I've given away my answer. I was going to say to you, is this an exothermic or an endothermic reaction? Not realizing that I've given you the answer already in the heading. Why is this an exothermic reaction? We have to look at the energy of the reactants and products. So here, the energy of my reactants is higher on the y-axis than the energy of my products, which means that if I calculate delta H, remember from last year, delta H means enthalpy change. Delta H is always the energy of products minus the energy of reactants. So if I want to calculate delta H, let me just change color here. Delta H will always be the energy of products minus the energy of my reactants. And in an exothermic reaction, delta H is always going to be a negative value. Why? Because my products have got less energy than my reactants. So when I subtract the energy of my reactants from the energy of my products, I will always end up with a negative value. And the shape of the graph for exothermic always shows that the energy of the products is below the energy of the reactants. Please also remember this energy here, the amount of energy absorbed in order to start the chemical reaction is your activation energy. And we spoke about activation energy a couple of slides ago. All right, now we move on to a very, very important graph. It is not a graph that's familiar to you. It is called the Maxwell-Boltzmann distribution curve, right? The Maxwell-Boltzmann distribution curve. Now, I'm going to put this into simpler terms for you. If you all wrote a science test a week ago, and your teacher marks your test, and instead of just listing your results, your teacher decides to draw a graph representing your marks, you would get a graph that looks fairly similar, right? Except that on the y-axis, you'd have the number of learners, and on the x-axis, instead of kinetic energy, you would have your marks. Now, if I drew a line there on your mark graph, this mark that you get on your x-axis would be the class average for that test. Why? Because the majority of students achieved that particular mark. Right. So you can draw a distribution curve like this for almost anything, and it allows us to see what the average is going to be. So if we look at this graph, let's take it back to science. Leave your marks behind for a moment. If we take this back to science, this Maxwell-Boltzmann graph, on the y-axis is the number of particles, in other words, the number of particles of a reactant in a chemical reaction. And on your x-axis, we have kinetic energy. Now, the majority of these particles, the reactant particles, have got a kinetic energy that falls here on the x-axis. So in other words, that's the average kinetic energy of the particles. Now let's go back to grade 10. What is average kinetic energy a measurement of? It's the temperature, which means that the majority of these particles have got a fairly low temperature and therefore a fairly low average kinetic energy. These particles here are the only particles that have a high kinetic energy. But if we read that off of the y-axis, you'll see that it's a very small number of particles that actually have a high kinetic energy in the sample of reactant. Now, let's fill in a couple of extra features onto our graph. Let's draw in the activation energy for this reaction. So, in this reaction, my activation energy falls on that position on the x-axis. This reaction requires so much kinetic energy in order for the reaction to occur. Now, if we look at this graph, only these particles here in the shaded section have actually got sufficient kinetic energy in order to take part in the reaction. All of these ones here, all these particles, have got a kinetic energy that is less than activation energy. So no matter how many times they collide with each other, they will not react because they do not have sufficient kinetic energy. And the collision theory tells us that for a collision to be effective, for a chemical reaction to occur, the particles have to have a kinetic energy equal to or greater than the activation energy. And none of these particles have sufficient kinetic energy. So only a very small percentage of these reactant particles will actually take part in the chemical reaction. Now the question is, how can I change this? How can I cause or have a scenario where more particles can now take part in the chemical reaction? There's two ways of doing that. The first way is to ensure that more particles have sufficient kinetic energy. Now, what do I need to do to a substance in order to increase its average kinetic energy? I heat it. I increase the temperature. So if I increase the temperature of this reactant, the shape of the graph is literally going to change. And I'll end up with a graph that looks something like that. Same number of particles, but this time there are more particles that have sufficient kinetic energy. So in other words, more particles that can now take part in the chemical reaction because they have an energy greater than activation energy. So what did I do? By changing temperature, I changed the shape of the graph. If you all go home and study really hard as a class, and you all improve your science mark, your mark distribution curve will also change shape like this. And your average, instead of being there, will now be there. So you have increased the average kinetic energy of the particles. How did we do that? By increasing temperature. So that is the first way of shifting or changing a Maxwell-Boltzmann curve, is to literally change the shape of the curve by increasing temperature. And by increasing temperature, we increase the number of particles that now have sufficient kinetic energy to take part in the reaction. The second method is actually a simpler method because the shape of our graph is not going to change. How do we increase the number of particles with sufficient kinetic energy, in other words, energy greater than activation energy, without changing the shape of the graph? We simply shift the activation energy. So if I move this line of activation energy to that position there, suddenly all of these particles now have energy greater than activation energy. But how do I do that? I add a catalyst. Now let's see who can remember from grade 10 and grade 11. What does a catalyst do? A catalyst offers a pathway of lower activation energy. So in other words, it lowers the activation energy for a specific chemical reaction. And by lowering the activation energy, it now means that more particles have got sufficient kinetic energy to take part in the reaction. Right. So those are your two methods of using a Maxwell-Boltzmann curve in order to change the rate of a chemical reaction. Change the shape of the graph by changing temperature, and move the line of activation energy by adding a catalyst to the reaction. Right, there's a much better picture than the one I drew. I don't know why I try and draw these things when I've got it so nicely done here. This is at the original lower temperature, where the average kinetic energy is fairly low. I now increase the temperature, T2, and at an increased temperature, I increase the average kinetic energy. And I now have more particles with sufficient kinetic energy to react. In the second example, instead of changing the shape of my graph, I simply shift the position of the activation energy by adding a catalyst. Now, the second factor that we spoke about in the collision theory was correct orientation. Now, ladies and gentlemen, please don't go home and learn all of these. This is just an example to show you what is correct orientation and what isn't. Now, this diagram might be fairly familiar to you because it comes from organic chemistry. This is ethene, 2 carbons with a double bond in between, so that is ethene. And this would probably be hydrogen chloride that is now bonding, hydrochloric acid, which now wants to bond with the ethene. Now, in the first example, the chlorine collides with the carbon atom, and they simply bounce off. Why? Why does a chemical reaction not occur in this example? Because for a chemical reaction to occur, existing bonds need to be broken. And here, the two atoms have simply collided with each other without the chemical bond being affected. In the second example, 2 hydrogen atoms collide with each other. Again, not an effective collision, not the correct orientation. However, in this third example, the hydrogen atom literally collides with the double bond between the carbon atoms. And during that collision, that double bond is broken. And during the breaking of the bond, now new bonds can form. So that was the correct orientation for the reaction to occur. But as I said, please don't go and learn these. Right? You are not going to be asked specifically about correct orientation. All right, now we are going to use the collision theory to look at each of the macroscopic factors and how each of those macroscopic factors affects the rate of a chemical reaction. And I am going to pretty much give you a 4-step recipe for answering these questions. And if you follow that recipe, if I can put it that way, you should get your marks every time. These will be worth between 2 and 4 marks at a time, right, when we discuss. So the question would be, explain how an increase in temperature affects the rate of a chemical reaction. Right. Now, first of all, when you increase temperature, you increase the average kinetic energy of the particles. Think of the Maxwell-Boltzmann curve, which means that more particles have sufficient kinetic energy to take part in the reaction. In other words, their kinetic energy is now greater than activation energy. So more particles or molecules have sufficient kinetic energy, which means that there are more collisions per unit time. Imagine if I told all of you where you're sitting now to stand up and start running around. You're not allowed to leave the room. You can run around in the room where you are. The faster you run, the more likely you are to collide with the people around you. If you're walking slowly with no kinetic energy, it's easy to avoid collisions. But when you're running around with a lot of kinetic energy, you're going to collide with each other, which means by increasing temperature, I increase kinetic energy. When I increase kinetic energy, there will be more collisions in the same amount of time. Please make sure you put in per unit time, because remember we're talking about reaction rate, which is per time. So there are more collisions per unit time. Now, if there's more collisions, it obviously means that there'll be more effective collisions per unit time. Not just collisions, but effective collisions per unit time. And what does effective collisions bring about? A chemical reaction. So if I have more effective collisions per unit time, I will have an increased rate of reaction. Right, so let's look at that again. A higher temperature increases the average kinetic energy of the particles, which means that more particles have sufficient kinetic energy to take part in the reaction, which means that there are more collisions per unit time, which means that there are more effective collisions per unit time, and therefore an increase in the rate of the chemical reaction. Right, 4 points to remember when answering questions on temperature and rate of chemical reaction. All right, let us now look at the effect of concentration on the rate of a chemical reaction. Now remember what concentration is. Concentration is the number of particles in a specific volume. Now I'm going to use a silly example. You've made a mess in the kitchen. You cooked lunch when you got home, you were hungry, and you've made a mess in the kitchen, and you now want to clean up. And you use a fairly cheap detergent, soap, to wash off the counters. Now, cheap soaps are cheap because they have a low concentration of the active ingredient, which means that when I place that soap onto a blob of grease or fat or tomato sauce, whatever it is that you've messed on the counter, there are only a few molecules that can react with the stain on the counter. In other words, there are very few collisions, which means very few effective collisions. So that detergent is not going to clean your counter very well. However, if I use a more concentrated cleaner, that means that there are more active ingredient particles in the same volume. If there are more particles, it means that there are more collisions per unit time. If there are more collisions per unit time, it means that there are more effective collisions, and therefore we increase the rate of the chemical reaction. So a higher concentration means more particles per volume, which means more collisions per unit time, more effective collisions per unit time, and therefore an increase in the rate of the chemical reaction. You see what I mean about a little recipe for answering these questions? Right, very similar each time we answer it. Next one, surface area. Right, what effect does surface area have on a chemical reaction? Let's go back to the kitchen. You cook a potato when you get home for lunch. Now, if I take that whole potato and place it into boiling water, it's going to take a long time for that potato to cook. However, if I cut the potato into smaller pieces, it cooks quicker. Why? Let's have a look. If the potato is whole, it is only the particles on the surface of that potato that come into contact with the boiling water. So the cooking reaction is going to be slow. However, if I cut the potato into smaller pieces, each of these pieces now has an entire surface where those particles are exposed to the water molecules, which means that there are more particles coming into contact with each other. Now, if I have more particles coming into contact with each other, what's going to happen? There will be more collisions per unit time because more particles are exposed to each other, the bigger the surface area. Therefore, there will be more effective collisions per unit time, which results in a higher rate of a chemical reaction. Now, let's take this away from cooking for a moment. How would we use this in a chemical reaction? Instead of using a strip of magnesium metal in a reaction, I use magnesium powder, because when I powder it, I've increased the surface area of the magnesium, and therefore the rate of the chemical reaction will increase. All right, finally, the addition of a catalyst. Now, I'm going to tell you a quick story about a catalyst. You may have heard the story already. Let's imagine that we live in a tiny little village, and this village is separated from the big city by a really, really big mountain. And the only way to get from the village to the big city is to climb over the mountain. So only the people who have enough energy can get to the big city. If you don't have the energy to climb the mountain, too bad, you're not going to the big city. Then one day, the people of the village decide to cut a road or a tunnel through the mountain, which means that people, even people with low energy, who don't have much energy, those people can now also walk through the tunnel and get to the big city. Does this mean that the original pathway over the mountain has been taken away. No, that original pathway is still there, but the tunnel has offered an alternative pathway, a different pathway for people to take to get to the big city. Now, ladies and gentlemen, that is what a catalyst does. A catalyst doesn't lower the activation energy of a reaction, but what it does do, it offers a pathway with a lower activation energy, so that even those particles that have a low kinetic energy can take part in the chemical reaction. Right, so catalysts do take part in the chemical reaction, but they are not used up or changed during the chemical reaction. They simply offer a pathway with a lower activation energy. Right. The notes that I've been working from do give a nice diagram. I'll show it to you now. When a catalyst is added, a path of lower activation energy is provided. More particles have sufficient kinetic energy to take part in the reaction. Therefore, there are more effective collisions per unit time because the activation energy is now lower, or there is a pathway of lower activation energy. Right, remember from last year, your potential energy graph? This reaction here, this pathway, is the reaction pathway without a catalyst, which means that this is my activation energy without a catalyst. But with a catalyst, I now have a pathway with a lower activation energy. Please remember that adding a catalyst does not change the energy of the reactants or the energy of the products, which means that it does not change delta H. It will only influence the activation energy of the reaction. They like to ask these. All right, so they ask you, they will give you the original graph. They'll say, redraw the graph in your answer book, and then redraw on the same set of axes the potential energy graph for the reaction with a catalyst. Right, they really enjoy asking that question. Right, here's the example. Right, I prefer my example of people having to climb the mountain to get the big city, but the same idea. Here, that boulder or the rock has to be rolled over the hill. Takes a lot of energy. Here, it can simply move through the mountain, through the tunnel. Right, different pathways. All right, I am now going to skip through a few of these. All of these are from your Macmillan textbook. Macmillan textbook has got some lovely examples. If your school uses the Macmillan textbook, go and look at some of these examples and the exercises and activities. They are really worthwhile. But I want to now look at an exam question. All right, this question comes from November 2010. All right, November 2010, so we're going back quite a while with this question. Now, I'm just going to give you a quick idea of what this experiment involves. During this experiment, sodium thiosulfate is placed in a solution of hydrochloric acid, right? So we add sodium thiosulfate solution to a solution of hydrochloric acid. And one of the products that is formed is sulfur. And sulfur is insoluble. So what happens is that that sulfur precipitates out. And the sulfur forms a yellow layer, a layer of yellow solid on the bottom surface of the Erlenmeyer flask, right? So how do we determine the rate of a chemical reaction using sodium thiosulfate? Basically, we take an Erlenmeyer flask or conical flask in which we have placed sodium thiosulfate. We then add hydrochloric acid to that flask and start a timer or a stopwatch and record how long it takes for us to no longer be able to see through the surface of the bottom surface of that flask, right? So basically, as soon as a thick layer of sulfur is formed, we can no longer see through the bottom of that Erlenmeyer flask, and we can no longer see what is on the desk beneath it. And the time taken for that to happen allows us then to record the rate of the chemical reaction. All right, so what do the students do? They add 5 cubic centimeters of hydrochloric acid to 50 cubic centimeters of sodium thiosulfate. The temperature of the mixture is 30 degrees Celsius. They measure the time it takes for them no longer to be able to see that cross that is being placed under the flask. The experiment is repeated with the temperature of the mixture at 40 degrees Celsius, 50 degrees Celsius, and 60 degrees Celsius, respectively. So what is going to be kept constant here? They are not going to change the concentration of the reactants. But what are they going to change? The temperature of the reactants. So in other words, these learners were trying to determine the effect of temperature on the rate of a chemical reaction. Right, question 6.2.1. Write down a possible hypothesis for this investigation. Right, now remember that a hypothesis always has to speak about, let's change that color. It always has to speak about the relationship between two variables. Now, what are our variables? The learners are looking at the effect of temperature on the rate of reaction, the rate of a chemical reaction. So what does our hypothesis need to include? The relationship between temperature and the rate of a chemical reaction. Now, we know that an increase in temperature increases the rate of a chemical reaction. Right. So our hypothesis would be increasing temperature increases the rate of a chemical reaction. Right. Speaking about the relationship between the two variables. 6.2.2, write down the name or formula of the product that requires the need to work in a well-ventilated room. In other words, this was carried out in a room where all the windows and doors are open. Why? Because one of the products is sulfur dioxide gas. And whenever you have a gas as one of your products, you need a well-ventilated room. So ladies and gentlemen, when they ask you about ventilation, it's always going to be because of a gas that is formed, right, that needs to be taken out of the room. 6.2.3, apart from the volume of the reactants, state one other variable that must be kept constant during this reaction. Now, we need to now say, okay, of those 5 macroscopic factors, we are looking at the effect of temperature on reaction rate, which means that all of the others need to stay constant. So what were the others? We've already spoken about volume, which actually is not one of the factors. Concentration. So the concentration of my reactants must stay constant. Right. We can only look at the effect of one factor at a time on the rate of a chemical reaction. So what needs to be constant? The concentration of your reactants. Why will we not speak about surface area? Because surface area only refers to solids. And if we look at our reactants, they are both aqueous solutions. So there's no solid that we need to look at. Also, we would not add a catalyst to this reaction. Right, write down the name or formula of the product that causes the crust to become invisible. So what causes that precipitate on the bottom of the flask? It is the sulfur that we spoke about. 6.2.5 says, why is it advisable for the same learner to observe the time that it takes for the crust to become invisible each time? Because ladies and gentlemen, you need it to be a fair test. Right, so you need the same person to be observing each time in order for it to be a fair test. Then the main reason why I included this question in this example is the graph. It says the graph below is obtained from the results, and it's a graph of 1 over time versus temperature. Very importantly, not time versus temperature, 1 over time versus temperature. 6.2.6, what is represented by 1 over time? Right, very important question. Anything divided by time, and we did this in grade 10, gives us rate. So what is 1 over time? It's the reaction rate, right? The rate at which the reaction took place, right? So anything over time always gives me the rate of the reaction. 6.2.7, what conclusion can be drawn from the results obtained? Now, ladies, if we look at our graph, as the temperature increased, so did 1 over time. Right? As my temperature increased, so did 1 over time. But what is 1 over time? 1 over time is reaction rate. So what is the conclusion to this investigation? As the temperature increases, the rate of the chemical reaction will also increase. And remember that your conclusion always has to tie back to your hypothesis, where we spoke about the relationship between temperature and reaction rate. Right. Now, this question was taken from November 2013, also an important question. Hydrogen peroxide dissociates at room temperature according to the following equation. You did this practical in grade 10. It was one of your prescribed practicals. Hydrogen peroxide gives you water plus oxygen. During an investigation, learners compared the effectiveness of 3 different catalysts on the rate of decomposition of hydrogen peroxide. So what is the aim of the investigation? To determine the effect of a catalyst on the rate of a chemical reaction. They place equal amounts of hydrogen peroxide into 3 separate containers and then add equal amounts of 3 catalysts P, Q, and R. And then they measure the rate at which oxygen is produced. Why do they measure the rate at which oxygen is produced? Because they are measuring the rate at which a product is formed. The quicker the product is formed, the higher the rate of the chemical reaction is going to be. For this investigation, write down the independent variable. Now, please remember that your independent variable is the variable that we manipulate, the variable that we control. What did we control here? We controlled the catalyst that was placed into each of those containers. So the independent variable will be the type of catalyst. Now, what did that influence? What changed because of the type of catalyst that I produced? The amount of oxygen that was produced. By putting different catalysts into different containers, I changed the rate at which oxygen is produced. So my dependent variable would be the rate at which oxygen is produced. Right, or the volume of oxygen produced. All right, the results are shown in the graphs below. So for each of them, we have got R, P, and Q. Each of them produces the same amount of oxygen. That is very important to remember, that the same amount of oxygen will be produced in each of these cases. But how quickly that oxygen is produced will depend on the catalyst that is used. 6.2. Which catalyst is the most effective? Give a reason for your answer. Now, my answer here would be catalyst R. Why? All 3 catalysts produce the same amount of oxygen. But which one produces that amount of oxygen the quickest? In other words, what are we going to look at? We need to look at the gradient of our graph. The steeper the gradient of a reaction rate time graph, the greater the rate of the reaction. So if I look at R, P, and Q, R has the steepest gradient at the beginning of the reaction, which means that R's reaction rate was higher than for P or Q. 6.3, fully explained by referring to the collision theory, how a catalyst increases the rate of a chemical reaction. So now we go back to that theory that we spoke about, the little recipe that we spoke about. What does a catalyst do? You first say that a catalyst provides an alternative pathway of lower activation energy. Therefore, there will be more effective collisions per unit time, and therefore the reaction rate will increase. Right, follow the little recipe. Make sure that you answer in a nice, complete way. In another experiment, the learners obtained the following results for the decomposition of hydrogen peroxide. Right, and that's now tabulated. Calculate the average decomposition of H2O2 during the first 400 seconds. So we now look at this section of our table. Right, during the first 400 seconds, what was the average rate of decomposition of hydrogen peroxide? Right. Remember in one of the first slides that we did, we said rate of reaction is equal to the change in concentration of reactants over change in time. So now from my table, I can look at the change in concentration of H2O2 divided by the change in time. Right. So if we do that as a proper calculation, right, the change in concentration of reactants over change in time. The change in concentration, remember we're always going to, sorry, can we just take that out?
I'm sorry, just while we start, we have 15 minutes now, 5-0.
Okay, well, this is my last example, so this one's going to be slightly shorter. Okay. Right, so reaction rate is the change in concentration of reactants over change in time. So from our table, we'll see that my concentration changes from 0,0200 to 0,0131. So that's the change in my concentration. And what was the change in time for that? It was during the first 400 seconds. Right. Let us look quickly at the mark allocation. I want to show you the memo. Sorry, it's not very clear. The mark allocation will be for your 2 substitutions and then 1 mark for your final answer. Then 6.5. Will the rate of decomposition at 600 seconds be greater than, less than, or equal to the rate calculated in question 6.4? Give a reason for your answer. Right. Now, ladies, what is happening at this section here? As the reaction progresses, my hydrogen peroxide is being used up. That's what happens during a chemical reaction. My reactant is now being used up. So the concentration of my reactant is decreasing. According to the collision theory, if I decrease the concentration of my reactant, there will be fewer collisions per unit time, which means that there will be fewer effective collisions per unit time, resulting in a lower reaction rate. So as the reaction progresses and my reactants start getting used up, the reaction rate slows down. So my reaction rate is always the greatest at the beginning of a reaction when I have high concentrations of my reactants. As soon as those concentrations start to decrease, the rate of my chemical reaction will also decrease because there will be fewer effective collisions. Right. Then 6.6, I'm not going to do with you now. It is a stoichiometry question. So that is one that I'm going to leave with you to do because stoichiometry is grade 11 revision. Right? So you should have gone through the stoichiometry. It says calculate the mass of oxygen produced in the first 600 seconds if 50 cubic centimeters of hydrogen peroxide decomposes in this time interval. Right. All I'm going to do to get you on your way, again, you must sit together in groups and work on this one. Please remember stoichiometry. There are 4 steps involved in stoichiometry. Step 1, you write a balanced equation for the reaction, which has been given to you at the beginning. Step 2, you convert what has been given to you into number of moles. Right? Convert what has been given into number of moles. Then you use your mole ratio from your balanced equation. And then step 4, convert your number of moles back into what is being asked. So in this case, you convert your number of moles back into the mass of oxygen produced. So I'm going to leave you with that one. The answer will be given on the board. And I hope that you find it a bit of a challenge, that it's a good way to round off this session. Thank you for listening and for watching. I wish you the best of luck for paper 2, now in the June exam, as well as later on in the year. Good luck.